Okay, well, hi everyone. My name is Lieke van Son. I'm a second year graduate student at the CFA at Harvard Smithsonian. I'm also affiliated to Amsterdam. And I will be discussing today which way did the wind blow? Namely, how can we probe stellar winds and cosmic star formation with binary black hole mergers? Um, so the bigger question that I really want to answer, that I think, really want to answer is, what can we learn about stellar physics from all of those merging binary black holes? And if you're a skeptic and you think, why should we use binary black holes to learn about massive stars? I want to remind you that maybe today we only have about 50 binary black hole detections or gravitational wave detections, but in a mere decade, third generation detectors are going to give us 10 to the fourth binary black holes per year, and they're going to be spread out all over the universe up to extremely high redshifts. So we'll be probing the evolution of massive stars by probing and understanding the distribution of merging binary black holes, just because we have such sheer numbers of detections. But this is a pretty big question. And of course, I won't be able to discuss even a slight bit of this in 10 minutes. So I want to focus on this question of how stellar winds and the cosmic metallicity evolution or cosmic star formation affect the merging binary black hole distribution. Or in more detail, what I want to show you today, or what I want to answer in this talk, is how do Wolf-Rayet winds and cosmic star formation affect the binary black hole mergers that we see exactly today at redshift 0. And these three things, I want to convince you that this is a really intertwined story, because we cannot think about cosmic star formation or the metallicity evolution of the universe without thinking about the massive stars that precede these binary black holes, because they're the main cause of metal enrichment throughout the universe. The metal enrichment then again determines the winds of stars that are born with these newer metallicities, which then again affect the binary black holes that you get. So zooming in a little bit about how do you get a binary black hole merger, I'm focusing my work on specifically on binary black hole mergers that come from isolated binaries. But even within the channel of isolated binaries, there's several subchannels. I'm showing here the classical channel, that is the channel that contains at least one common envelope to bring the stars and black hole closer together. But even within this set series of events that you need to get a binary black hole merger, many uncertainties remain. But one of the main uncertainties on the massive stellar evolution part might be these stellar winds, and specifically Wolf-Rayet winds. You can see that there's two phases in this evolution where Wolf-Rayet winds play a major role in the life of the life of a binary black hole merger. So massive stellar winds, we've heard a lot of beautiful talks this week already, but why are they important for these black holes? Well, not only do they affect the final black hole mass that you get, but of course, the stellar winds can also affect the radii, which can cause or prevent interaction. They can widen the binary. And last but not least, they're thought to be metallicity dependent, at least the radiatively driven winds, which nicely overlaps with the metallicity evolution of the universe. So you might have heard from people saying that to form these 30 solar mass black holes that we see with LIGO and Virgo, or even higher mass, we need metal poor progenitors. So this raises the question, when do metal poor stars form? And to answer this question, I'm going to show you the metallicity specific star formation rate density. Now that's a whole mouthful, but that just means that I'm going to show the metallicity distribution on the y-axis as a function of time, where this is look back time in gigayears. So we live somewhere here today, and the Big Bang was somewhere here in the beginning, or redshift space if you prefer. And we don't actually know what the distribution is of metallicities because it's very difficult to constrain, but we know that it should have started out somewhere metal poor at the Big Bang. And as stars enrich the universe with metals, we should have ended up somewhere around solar metallicity today. Again, there's multiple ways to estimate a metallicity distribution throughout the universe, but what we're doing in this work is using the TNG simulation, a cosmological simulation, um, and we fit our metallicity distribution to this. So what's shown in yellow is the amount of solar mass formed per year per gigaparsec, sorry, per megaparsec squared cubed throughout the age of the universe. Now, what we can do is fit an analytical function to this, which we do following Kuhn-Neisel's paper from 2019. And specifically, this is a log normal distribution that evolves with redshift. And voila, we have some sort of answer for the question, when do stars form with what metallicity? But that's only half of the question, of the answer, of course, because to really know what's going on, we should now know at what metallicity black hole progenitors like to form. So to answer this question, I've used a binary population synthesis code called COMPASS, which basically allows me to transform a lot of initial assumptions into a distribution of final masses and delay times. And I want to highlight the Wolf-Rayet winds that we use, which are from Hamann and Kuserke in 1998. But as a lot of you might know, there's a lot of uncertainties, or there's large variations in the predictions for Wolf-Rayet winds. So what we do to mimic these variations is we vary over this gray band in Wolf-Rayet strength. So we take 5 times and a 10th time the strength in Wolf-Rayet winds. So back to this image, what I'm going to show now is the progenitor location of stars that will form merging binary black holes exactly at redshift 0. So what that means is that, for example, if a binary was born about 10 gigayears ago at a metallicity of 10 to the minus 3, and this binary successfully formed a binary black hole, and this binary black hole then took another almost 9 gigayears to merge at redshift 0, then I'm going to draw a blob or a dot all the way over here. So this is what that looks like for a fiducial set of assumptions in COMPASS. Now, this is still a little messy, so I'm drawing some contours over this to make a little bit more clear what is happening. And this is a really interesting result already, because as you might see, notice, only the parts where the blue curves and the yellow curves overlap do we actually expect not only to form stars that with this metallicity, but also have these stars form black hole binaries that can merge at exactly redshift 0. So this is really interesting because what this shows is that even though black holes indeed like to form at slightly lower metallicities in general, the cosmic star formation history mostly favors to form stars at higher metallicities throughout the largest time of the universe. And this means, or this implies, that the delay times of these binary black holes really matter. So the distribution that we're going to observe at redshift 0 will be dominated by systems that have a high metallicity or a short in-spiral time and a short in-spiral time, or form with low metallicity but have a significantly longer in-spiral time. So this means that getting this cosmic star formation rate density correct, these yellow curves, really matters. And this has also been shown in great work that I want to point you to from Krusninska and Neisel, Boko, and Broekgaarde, from which the second paper is in preparation. But all of this was assuming one variation of Wolf-Rayet winds. And I just showed you that Wolf-Rayet winds are not that certain at all. So what happens if we vary the Wolf-Rayet wind strengths? So again, this is the same image for a fiducial Wolf-Rayet wind strength. Now I'm going to enhance the Wolf-Rayet winds. So this is twice the Wolf-Rayet wind strength or 5 times the Wolf-Rayet wind strength. And what we see is that the distribution of black hole progenitors lowers in metallicity. Now, if we decrease the Wolf-Rayet winds, so we go to half, thank you, or a 10th, we see that the exact opposite happens. So we increase the metallicity at which we can still form black holes. So takeaway point 2 is that Reducing the Wolf-Rayet winds enables binary black hole formation from progenitors at much higher metallicities. And there's a specific population of stars that contributes largely to the binary black hole mergers that we would see today, which have very short delay times and high metallicities. So I looked a little bit further into where these come from, because obviously there's a lot of ways in which Wolf-Rayet winds can interact with this whole complicated process of forming a binary black hole merger. And I found that it's mostly step 3 and 4 that cause this difference. Namely, what happens if you increase the Wolf-Rayet wind is you lower the progenitor mass of the supernova. So what I'm showing here is the same system from the moment that it becomes a helium main sequence star. So when we start to use Wolf-Rayet winds, onwards until it's a compact object for a large variation in Wolf-Rayet winds. And you see that if we increase the wind, we basically lower the pre-supernova core mass. And in the assumptions that we use right now, these lower CO core masses are expected to receive a supernova kick when they form. And the kick in this system is significant enough to unbind the system, leaving you with no black holes, binary black hole, whereas the opposite is true for reducing the Wolf-Rayet winds. So in conclusion, I want to just, if you forget everything else, I want you to remember that for binary black hole distribution, both the winds and the cosmic star formation are very important. And reducing the Wolf-Rayet winds enables black hole formation, binary black hole formations from progenitors at much higher metallicities. And stay tuned for the rest of this paper, which hopefully comes out in a couple months, where we not only vary the Wolf-Rayet winds, but also cool giant winds and the star formation history. And we will try to compare directly with the rate estimates from LIGO and Virgo. Thank you very much for sticking with me until Friday, 5 p.m. And I hope let me know if you have any questions.